This lecture will be over Chapter 19, Section 8. I'm going to discuss RC circuits, RC being resistance, capacitance. So when a capacitor is charged by a battery in series with a resistor, that's where we're going to start. We got a battery here, we have a resistor here, which the current is going to meet before it goes through and finally hits the capacitor. When it hits the capacitor, obviously we've got a buildup of charge here, which means we've got a negative buildup of charge over here, and then we have the current going around in the closed circuit, finally making its way to the battery. So the current and the capacitor charge are not constant. The charge is going to vary with time. This is going to accumulate. It's going to take time to build up. As it builds up, you're going to see a voltage increase here, and as the voltage increases here, the voltage is going to decrease here because the current is going to drop. How do we gauge how much charge is building up here? Well, not to put too fine a point on it, this is going to be the formula in which we will determine that. We have the Q final, and then we have an exponential term over here with this RC right here, and that is going to refer to a specific time. In that time, there's a significant change in the charge on the capacitor. The time is called the time constant or the relaxation time, and it's the same for charging or discharging. When it comes to the current, you're going to see the RC employed here, and you're also going to see it employed here. What you're also going to see is that both I or Q as measured current or charge, you're going to see that the current will drop here. I mean, initially it shoots up, but then it's going to drop off over time, and then you will see the charge build up over time on the capacitor. That's how these circuits work. So initially, whenever you start out with an RC circuit, time 0, you've got no current, you've got no charge, the switch is open, nothing's going on. Boom, switch gets closed. So what happens next? Charge on the capacitor increases, and you also have current going through the resistor. We're going to ignore any inter-operations of the battery source. We're just going to say that it has an EMF of epsilon and be done with it. So at this time, from Kirchhoff's loop rule, the voltage across the resistor is going to be equal to the battery's terminal voltage, or epsilon. The initial current through the resistor is going to be given by this. Now, the initial capacitor charge, which is going to be called this, is going to be 0. We're going to denote the time varying current and charge as little I and little q respectively. In other words, those are going to vary with time. So as the capacitor charges, its voltage increases, so the potential difference across the resistor must decrease, so corresponding to the decrease in the current. From Kirchhoff's loop rule, the sum of these two is constant and equal to the battery EMF. In other words, the potential difference you have here should be the same as what the battery is providing. After a long time, the capacitor becomes fully charged, the current decreases to 0, potential difference across the resistor becomes 0, and the entire battery voltage appears across the capacitor. Thus, the capacitor charge and the current vary with time as shown in these diagrams, which is the same thing as what we had before, except we're going to color this in with a little bit more detail here. You can see the initial current divided by 2 ends up here. The initial current divided by E ends up being right about here, and this is where we're going to get the value of time, which is referred to as RC. That RC is going to be the same time here if we look at charge. So the charge on the capacitor increases exponentially with the time towards the final value of Q final. It never actually quite reaches it. It's more of an asymptote, but that's what it theoretically would end up being. So to obtain a detailed description of the time variation of the charge and current of the circuit, we would need to solve equation 1916, this one right here, which is a differential equation for the charge Q and the rate of change I. Those the solutions are going to end up containing the exponential function e to the minus t divided by RC, where e is equal to 2.178. There's a lot of details with that. We're not really concerned with that. We're really concerned with really the final product. What we find out is that if the switch is closed when we start, then the current I and the charge Q vary with time according to these equations. So note the initial current and note the final charge. So the graphs and the equations of figure 19.34, which let me see if I can find those. Let's be up here. These figures right here. These equations right here are graphed here. That's the point of that. The graphs and the equations both show that as time goes on and the exponential function approaches 0, the capacitor charge Q approaches its final value, and we're going to call it that. The current decreases and eventually becomes 0. When it's 0, we find out that the EMF is going to be equal to Q over C, and that Q is going to be equal to C times E if you rearrange this. We're going to note that the final charge doesn't depend on the resistance, although the rate at which the final value is approached is slower when R is large than when it's small. So if we return back to figure 19.34, this right here, we're going to notice that at the instant the switch is closed, the current jumps from 0 to its initial value. After that, it decreases and gradually approaches 0. The capacitor charge starts at 0 and eventually gets to this point. In other words, current goes up and then go down. Charge always goes up. After that, it decreases. Okay, all right. After a time, t is equal to RC. The exponential functions have the value of this. At this time, the current has decreased from its initial value to 1 over E of that value, and the capacitor charge has reached this of its final value. The product RC is therefore a measure of how quickly the capacitor charges. So this is going to be called the time constant, or the relaxation time of the circuit, and it's denoted by the Greek letter tau. When tau is small, the capacitor charges quickly. When it's larger, the charging takes more time. The horizontal axis, where this is an asymptote for the curve, is in the first figure we looked at. Strictly speaking, I never becomes precisely 0, but the longer we wait, the closer it will get to that. So if we wait 10 times RC, then the current has decreased to this fraction of the initial value. Similarly, the curve in the charge part of that approaches the horizontal dashed line here as an asymptote. So it gets very, very close. We could carry out similar analysis for the discharge. The results are going to be very similar. So if we're discharging, then we can measure the current as well as the charge. And these are going to be the initial values on the discharge. So I thought that was kind of neat. And these are the dissipation of the RC circuit of charge and then the current. So I hope you got something out of that. I thought it was kind of neat.